After studying this module, you will be able to know more about formation of symmetry adapted linear combination of atomic orbital. Learn how to use bond vectors as basis for developing SALC. Generate SALC for C3b point group. Learn how to use orbital functions as basis for developing symmetry adapted linear combination. Find SALC for D3H point group, and then after finding SALC, we will be checking their correctness, whether SALC so formed are correct or not. You have already know about the need for the formation of SALC, that is why they are needed. You have also learned the basis for the formation of SLC. SALC are simply the linear combination of base functions, but constructed in such a way that these SALC match the required symmetry. Group theory provides a way of generating SALC from some chosen functions. Task of SALC formation simplifies the process of making molecular orbital of the molecule. In earlier module, we have learned this systematic use of projection operator in generating SALC. In this module, we will continue for finding SALC for few more molecules, and I will explain this by just taking the examples also and with the help of your models. Now, let us take the example of ammonia molecule, and let us take in ammonia molecule the NH bond vectors R1, R2, R3 as the basis. These are shown in the figure, and we have to now find out how these R1, R2, R3 are the basis for generating SALC. Let us take ammonia molecule in which the NH bond vectors R1, R2 are used as the basis for generating SALC. Now, I will explain this with the help of the molecular orbitals or by just taking the this structure for this ammonia molecule. This is ammonia molecule and these are NH bonds in this. I will label these NH bonds as R1, R2 and R3, and I will see the effect of various symmetry operations of this ammonia molecule on these vectors R1 and R2. That is, I will just go for the transformation operator corresponding to this symmetry operation. In this molecule, the symmetry operations are E, C31, C32, sigma V dash and sigma V double dash. C3 is shown over here, and this sigma V I can just put down like this. There are three like this, one along this, another like this and third like this. So, I am having in this molecule C31, C32, E, sigma V dash and sigma V dash, and I will just now go for this effect of symmetry operations on these vectors R1, R2 and R3. Now, also we know that is the vector which is shifted by symmetry operation will contribute chi is equal to 0, and the vector which is not shifted will contribute chi is equal to plus 1, and the vector which is unshifted but direction is reversed, it will contribute chi is equal to minus 1. Now, in the table what we find the effect of various symmetry operation. Say for example, E means I am doing nothing on this. It means R1 remains R1, R2 remains R2, R3 remains R3. Now, C3, that is if I just give a rotation like this, that is C3 120 degree rotation, then what you find, all these R1, R2, R3, they are shifted. That is, R1 goes to R2, R2 goes to R3, R3 goes to R1. Like this, similarly we take the effect of C through, that is further C3 rotation, and we get like this. This table summarizes the effect of various symmetry operations on R1, R2, R3. Last row of this table gives me tau reducible, which gives me the figure as 3, 0, 0, 1, 1, 1, and I have explained to you how you can get this tau reducible, that is just by knowing whether the vector is shifted or whether is not shifted. Tau reducible, which is there, can be reduced to irreducible representation by following the standard reduction formula and by making use of the character table of C3.V group as given below. And after tau reduction, it comes out to be tau reducible is equal to A1 plus E. Using projection operator corresponding to A1 and E only, three base functions R1, R2 and R3. Now let us try to make use of projection operator corresponding to A1 operating on function R1, that is given by A1 P R1 Ni upon H summation R chi A R O R R1. If we make use of this, we get the characters as 1 by 6 within bracket 1 into R1 plus 1 into R2 plus 1 into R3 plus 1 into R1 plus 1 into R3 plus 1 into R2. That is, all symmetry operations of classes are to be taken separately as mentioned earlier. That is, if there are 3 sigma b's, I have to take separate R1, sigma B1, sigma B2 and sigma B3. Now this result comes out to be, after normalization as given in equation 1, 1 upon under root 3 within bracket R1 plus R2 plus R3. Now let us consider the effect of EP on R1, that is EP R1 is equal to 1 by 6 within bracket 2 into R1 plus within bracket minus 1 into R2 plus within bracket minus 1 into R3 plus 0 into R1 plus 0 into R3 plus 0 into R1, and the net result we get by equation 2 as 1 upon under root 6 within bracket 2R1 minus R2 minus R3. Now let us use transformation operator corresponding to A2 symmetry. The A2 is not a part of the reducible representation, so we should get no SALC corresponding to A2 symmetry, and let us check this. The effect of A2P on R1 gives the result as A2P R1 is equal to 1 upon 6 within bracket 1 into R1 plus 1 into R2 plus 1 into R3 minus 1 into R1 minus 1 into R3 minus 1 into R2. That is, net result is 0. That is, there is no linear combination of R1, R2, R3 which belongs to A2 symmetry. Same can be checked with other generating functions R2 and R3. Now we have to find out another linear combination of R1, R2, R3 which also has asymmetry, as it is two-dimensional in nature. For this, let us take R2 function and follow the similar procedure as described earlier, and let us operate PA1 on R2, and we get the same result, that is, after normalization we get same result as 1 upon under root 3 R1 plus R2 plus R3, that is, same SALC is obtained. Now, let us consider EP on R2, and after operating this EP on R2, we get the result as 1 upon under root 6 2 R2 minus R1 minus R3 as shown in equation 3. Let us now check the orthogonality of SALC so obtained during this over here. Two linear combinations are orthogonal to each other if the sum of the products of the corresponding coefficient is equal to 0. Take SALC of equation 1, that is R1 plus R2 plus R3, and SALC of equation 3, that is 2R2 minus R3 minus R1, and let us check their orthogonality as shown over here, R1 plus R2 plus R3, and below I am writing minus R1 plus 2R2 minus R3, and what we get, that is if you add these together we get the 0. It means these SALC that is given by equation 1 and equation 3 are orthogonal to each other. Now, let us check the linear combination given in equation 2, that is 2R1 minus R2 minus R3, and then equation 3, that is 2R2 minus R3 minus R1, and write these as 2R1 minus R2 minus R3 minus R1 plus 2R1 minus R3, and if we just add these together, what we find? It is not equal to 0, it comes out to be 3. It means these are not orthogonal to each other. All SALC obtained should be orthogonal to each other. If we take R3 function and use the E operator, projection operator, we get the following SALC as given in equation 4, that is 2R3 minus R2 minus R1. Let us check the orthogonality of 2R1 minus R2 minus R3 and 2R3 minus R2 minus R1. This equation can be written as 2R1 minus R2 minus R3 minus R1 minus R2 plus 2R3. And what is the result? It is not equal to 0. These are also not orthogonal to each other. Now, how to find out SALC which belongs to E symmetry and also orthogonal to other SALC? There is no simple method to get the third SALC of E symmetry in C3V point group. Now, we can obtain the second linear combination of symmetry E by taking the difference of the linear combination as given in equation 3 and in equation 4, that is 2R2 minus R3 minus R1, 2R3 minus R2 minus R1. And by taking this difference and after normalization, we get the function as 1 upon under root 2 R2 minus R3, equation 5. Now, let us check the orthogonality of SALC given by equation 5 with other SALC given by equation 1 and 2. If you take equation 1 and equation 5, we have to write down R1 plus R2 plus R3, and then we have to write down R2 minus R3. And if we do this procedure and then add this together, you find the result is equal to 0. Now, let us take then other SALC, again 2R1 minus R2 minus R3 and then R2 minus R3, and let us check their orthogonality. Again it is equal to 0. So, what we find over here, the SALC given by equation 5 is orthogonal to SALCs given as 1 upon under root 6 2R1 minus R2 minus R3 and 1 upon under root 3 R1 plus R2 plus R3. Thus, the three normalized SALC and their symmetry are given as 1 upon under root 3 R1 plus R2 plus R3 has A1 symmetry, and the other two SALC, that is 1 upon under root 6 2R1 minus R2 minus R3 and 1 upon under root 2 R2 minus R3 have E symmetry. That is, just by taking bond vectors we have found out this. Now let us take orbital function as the basis for getting SALC. We can make use of SPDF orbital as the basis and can develop SALC. These types of SALC are very important in connection with molecular orbital theory of transition metal complexes. Let us use pi orbital in cyclopropynyl cation, that is C3H3 positive, which has delocalized pi orbital system. Here we will see that how pi orbitals on individual carbon atom can be combined to give symmetry adapted linear combination. Projector operator method again will be used. Instead of checking projection operator for each and every irreducible representation of the point group, we shall check only OR corresponding to desired irreducible representation for getting the desired irreducible representation. To get the irreducible representation using pi orbital functions as the basis, and second reduce it to desired irreducible representation. The point group of C3H3 cation is D3H. Various symmetry elements and pi orbitals on each carbon atom in C3H3 cations are given in figure. Now let us take the model of C3H3 positive cation. Now in this I am just showing it over here, and this black and this white part, they are showing the pi orbital on each carbon atom. There are 3 pi orbitals. This is pi 2, pi 3, pi 1, pi 1, pi 2, pi 3. And I have to see the effect of various symmetry operation of the molecule of this point group. This is my C3 axis. I can rotate all these pi orbitals like this, all these pi orbitals like this. So in this D3H point group I am having this C3 axis, and also this molecule has sigma v like this, that is it is taking one of the pi orbital bisecting other 2 pi orbital. Similarly it is like this, and third it is like this. So I am having in this molecule this C3 axis and then 3 sigma v. Let us take this model and this effect of C3 operation on this p 3p orbitals. What happens after giving this rotation over here? I find all the p orbitals, they are shifted. So the contribution by these p orbitals when they are shifted is 0. If I take this sigma v, this and this pi orbital they are shifted, only this pi orbital is not shifted. So it will contribute +1 and this will contribute 0 to this. Like this we will take up all these symmetry operations of D3 point group and see the effect of various symmetry operations on these only 3 p orbitals, pi 1, pi 2, pi 3, and all the results for each and every symmetry operation is summarized in the table given. Table 1 gives the effect of transformation operators corresponding to various symmetry operation D3H point group on 3 p pi orbitals. For example, if we take the operation E, what you will find? Pi orbital, pi 1 remains pi 1, pi 2 remains pi 2, pi 3 remains pi 3, and the net effect overall is 3 because these are not shifted. If I take the effect C31 operation pi 1, pi 2, pi 3, they are shifted to other pi orbitals. Pi 1 goes to pi 2, pi 2 goes to pi 3 and pi 3 goes to pi 1. Like this, we can study the effect of various symmetry operations on pi 1, pi 2 and pi 3. And by doing this, what we get, the overall tau pi is 3, 0, 0, minus 1, minus 1, minus 1, minus 3, 0, 0, 1, 1, 1. How I am getting minus 1 result? Because when I carry out C2 operation, then these pi orbitals, they are inverted. Like this, we get the negative effect. And again, as I told you, if the pi orbital is not shifted, only its direction is reversed, that is, it remains at the same place, then it contributes minus 1. And following standard reduction formula, tau pi so obtained can be reduced to A2 double dash and E double dash. We have now to develop SALC corresponding to A2 double dash plus E double dash irreducible representation only. Again, we will follow projection operator method and corresponding transformation operators. Let us use the projection operator corresponding to A2 double dash on pi 1, that is A2 double dash P pi 1. And we will get, after doing this, the net result we will get as SALC equal to is 1 upon under root 3 pi 1 plus pi 2 plus pi 3. That is, after doing all these calculations, you will get this result. Now, let us apply A2 double dash on pi 2 and follow the above procedure as been discussed. Again, what you will get? You get the same result, pi 1 plus pi 2 plus pi 3. That is, we will not get different SALC. Again, apply A2 double dash on pi 3. You will get the same result, that is as pi 1 plus pi 2 plus pi 3. Therefore, all these projection operator P A2 double dash on pi 1 is equal to P A2 double dash on pi 2 is equal to P A2 double dash on pi 3 give me the same result as after normalization as 1 upon under root 3 pi 1 plus pi 2 plus pi 3, that is the results given in equation 6. Now, let us find the SALC corresponding to E, that is, I operate E projection operator on pi 1 and pi 2 and pi 3. Now, after operating on pi 1, I will get the result after all these calculations as pi 1 minus pi 2 minus pi 3. And the normalized SALC when E double dash is operating is 1 upon under root 6 2 pi 1 minus pi 2 minus pi 3 as given in equation 7. The SALC given in equation 7 is one of the two SALC corresponding to E double dash. To find the second SALC of E double dash symmetry, we have to proceed as follows. E double dash projection operating on pi P2, we get the result as 2 pi 2, 2 pi 3 minus pi 2 minus pi 1, that is equation 9. Similarly, we will get equation 8, 2 pi 2 minus pi 3 minus pi 1, that is we will get these two equations. And we have to check now the orthogonality of these SALCs obtained by equation 7, 8 and 9 with that equation in 1. For this, let us check this, and by checking what we find that we are not getting the right SALC corresponding. So, we take the SALC given by equation 8 and 9 which are orthogonal to SALC given by equation 7. To get the second SALC corresponding to E double dash, let us subtract SALC of equation 9 from the SALC given by equation 8 as shown below. And by doing this, what we are getting, the SALC unnormalized is pi 2 minus pi 3, or after normalization the SALC is 1 upon under root 2 pi 2 minus pi 3. That is, we are getting these 3 normalized SALC by using 3 pi orbitals on cyclopropenyl cation. And similarly, we can make use of other orbital functions as the basis for finding symmetry adapted linear combination of molecules. So, in this module, what we have learned? We have learned further about how SALCs are formed, using bond vectors as the basis for finding SALC, and we have taken over here the example of C3V point group, that is ammonia molecule, in which we have used NH bonds, that is R1, R2, R3 as the bond vectors, and we have seen under various symmetry operations how they are shifted, and by making use of that we got the tau reducible which has been reduced, and SALC corresponding to that have been formed. And we have now also taken the orbital functions on, that is pi orbital on cyclopropenyl cation, which has 3 pi orbitals, pi 1, pi 2, pi 3. And we have followed the similar procedure, that is, we have carried out the effect of symmetry operations of the point group, that is here D3H point group of cyclopropenyl cation. And after doing this, we obtained tau p reducible representation, which has been reduced to A2 double dash and plus E2 double dash. And by making use of this projection operator corresponding to this, we could develop SALC for these point groups also. Like this, we can follow number of other molecules.